Okay, it's 1 o'clock, so let's go ahead and get started today. So good afternoon, everybody. How's everyone doing on this fine Thursday afternoon?
Very good.
Good, thank you.
Good, good. Yeah, good. I'm glad everyone's doing well. Okay, so the plan today is we're going to finish up the first set of lecture notes I have here on just kind of basic cash flows and interest. So we're almost at the end, so I think probably won't take us the whole time to get there. And then we're going to start a new set of lecture notes on present worth analysis. Okay? But before I get started with any of that, are there just any questions I can answer maybe from last time or on the homework, or just any question you guys have? Okay. So at any time, if you have questions, if you think of anything, you can stop me anytime. You can turn on your mic or just send the question in the chat, and happy to answer. Okay, so let's just kind of briefly review what we did last time, because I think last time, there was kind of a lot of information. But I think the starting point from today is last time we started introducing this idea, different kinds of cash flow. Okay. It's important to characterize these different kinds of cash flows, and more importantly, it's going to be important to learn how to convert in between them, just so we can analyze kind of the financial and economic picture of engineering projects. Okay, so we've seen 3 so far. Okay, and so the first one that we've seen is a single lump sum in the present, and so we gave that the symbol P, right? So P for present. We also used, that was the, when we're doing examples last time, we used P for principal. So, they both mean kind of the same thing. But P just represents money that you have, that you would have today, right? Right. Another, the second type of cash flow that we went over was a single lump sum in the future. Okay? I remember we went over that formula between P and F, where something in the future will usually be worth, the money that you have now will be worth more in the future because of the interest rate. Okay, and then the third one that we went over was a uniform series. Okay? And so that was a a uniform series of payments that you would make every month, every year, or something like that. And A would be the amount that you actually paid out. Okay. Right. And so what we started going over, at the end of lectures last time was, how do we compute equivalent cash flows between all these different kinds? Okay. And so the first formula that we went over was the F and P formula. Right. So this is our compound interest formula, where we can use this formula to convert between a single lump sum in the present day and a single lump sum in the future, and vice versa. Okay. So if we drew the cash flow diagrams for this, okay. Okay. So if we drew the cash flow diagrams for this, say that we have a single lump sum in the present. Okay. And so with this formula, what we're able to do is kind of convert in between these two. Okay. So this would be our P, and this would be our F. Okay. So remember, a P is a single lump sum in the present day, and we used, in our cash flow diagrams, we used the time 0 to denote present day. So a single lump sum in the present day would be like, an up arrow or a down arrow, a single one that's on time 0. Okay. And then we can use this formula to compute the equivalent cash flow to something in the future, this would be F. Okay. So a single lump sum in the future, in terms of a cash flow diagram, would look like this. So it would just be a single arrow at some future date. In this case, it was 3, but it could be at any time. It could be at 1, 2, 3, 4, 5, 6. Okay. And the important thing is that, F just represents a single lump sum at some time in the future. Okay? And so this formula is basically used to convert in between these two different cash flows. Okay? All right, any questions on this? Okay. All right, so the next formula we went over, so that's converting between F and P. And so we need to get conversions between F and A and P and A. Okay, so let's do that. So I think the last example that we did last time was concerning this example, or this formula right here. Okay, so we have F is equal to A times 1 plus I to the n minus 1 over I. Okay, and so this is, because we have an F and we have an A here, we can use this formula to convert between a future sum and a uniform series. Okay? And so schematically, it might look something like this. Okay, so on this side, we would have a future sum. Okay, so a future lump sum would look the same as we did on the previous page. That would just be one arrow at some future date. Okay? Whereas a uniform series would look like this. So a uniform series, remember, is a uniform series of payments that you make at the end of the year, usually. So in this case, we're making the same payment at year 1, year 2, and year 3. Okay? So since all those payments are the same, this is the uniform series, so we call this A. Okay? And so we can use this formula to compute the equivalence between these two guys. And so basically what you can compute is you can compute, how much you would have to pay per month to have the equivalence of, one single future sum in the future like that. Okay, and this is taking into account interest rates too. And so that's the conversion between F and A. And so the last one that we need is a conversion between A and P. So we didn't go through this last time. So I'm just going to give you the formula. Okay?
Professor, I have a question.
Sure, what's up?
Before we move on, when you mentioned that it's usually a payment that we make yearly, but can it be also monthly?
Yes, yeah, definitely. So the uniform series, typically it's for engineering projects we consider that yearly, just because that's when all the finances are kind of summed up for the year. But you can use the exact same formula for like something that you would make monthly too. So the only thing is that, the uniform series is a payment that's the same in amount, but you make it at some regular intervals. So if you are making like if you can consider like your credit card bill, or not your credit card bill, your phone bill, or your internet bill, because that's the same every month. You would consider that like a uniform series because it's the same amount that you're paying at regular intervals. Yeah, I'll do one more example. I'll do kind of one more simple example with this formula right here, because we haven't used this in the example yet. But let me draw the cash flow diagrams for this guy. Okay. And so let's draw A first, because it's on the left-hand side of the equation. Okay. So uniform series would look something like this. Okay. So it's a uniform payment that you're making, at the end of every period. So it could be every year, every month, every week. Okay. And then, the P in this case represents just a single lump sum in the present day. Okay. And so you can use this formula to basically convert in between these two guys. Okay? And right after this, I'll do an example that kind of illustrates kind of a pretty common situation where you would use this formula. Okay? Before I do that, are there any questions on this and how these formulas, how do you, or just the conceptual understanding behind these formulas?
We're good.
Okay. Okay, so let's do an example with that, that last one, because we haven't really seen that yet. And so this is actually a very common situation, because if you think about it, you know, P represents the sum of money that you are, you know, that you obtain in the present day, and A represents a series of payments you make over time. So the most common, I think, situation for this is taking out a loan so that you can have money today, and then you would pay back that loan kind of steadily over time. Okay, and so let's think of a situation where, you know, you want to buy the latest, you know, iPhone, Galaxy phone, whatever. Okay, but you're short on cash. But you know your uncle has some money, right? So let's say that you want to borrow. You need to borrow 800 bucks from your uncle to buy the latest phone. Okay? Okay. So unfortunately for you, your uncle is an accountant, and so, you know, he'll lend you the 800 bucks, you know, but he's going to charge you interest rate on that money. So he makes a little bit on the side. So, you know, this is an uncle that maybe doesn't love you that much. Okay? And so your uncle says, okay, you know, I'll lend you the money, but you'll have to pay me back in uniform monthly payments. Okay. Over a year with a 5% interest rate. Okay. And so what you need to compute, just to make sure that, you know, your uncle's not scamming you, is you want to compute, you know, how much you have to pay your uncle every month. Okay. Okay, so let's break this problem down. So and so in order to purchase your phone, you need that $800 today. And so this $800, this represents a present sum, right? Because that's money that you need today to buy your phone, you know, today, right? And so let's define the interest rate. So the interest rate here given to us in the problem is 5%. And then the number of periods here, you know, it's not explicitly said in the problem, but, you know, we can compute it. So, you know, your uncle says you have to pay him back, you have to give him a payment every month, and this has to occur over a year. So, you know, we say that there's 12 months in a year, so n is going to equal 12 in this case. Okay. And then what we want to compute is we want to compute the uniform amount that we have to pay our uncle every month. So we know that a uniform series of payments is A. And so so in this problem, we're interested in computing A from all the other information that we have here. Okay? Okay. And so based on all the information, you know, we have P, we have I, and we have N. We know that we need to use our A and P formula. Okay. And so let's go back over here. And so luckily we have a formula for this. So this formula right here says, you know, if you have P and you have I and you have N, you can compute the equivalent uniform series of payments that takes the interest rate into account. So let's go ahead and do that. We say that A is equal to P. So P in this case is 800. Okay. Next, we multiply by the interest rate, right? Okay. So we have I, so this is going to be 0.05. times 1 plus I again, so that's going to be 0.05, raised to the n power, which is 12. Okay. And then we divide by 1 plus our interest rate, 0.05, raised to the 12, minus 1. Okay. So it's a little bit of a, you know, a lot of numbers to punch into your calculator. But once you do all that, you'll see that you owe your uncle $90.26 every month. Okay. So if your uncle comes to you and says, you know, with all the calculations, so you owe me $100 a month, you know that your uncle's BSing you, and you only owe him $90.26. Okay. This example may or may not be motivated by something that happened in my life. So, you know, always good to check your numbers. Okay. All right. Are there any questions on this example? Okay. And so, you know, I showed you all those formulas on the previous page, and you know they're configured a certain way. But remember, you can always kind of manipulate those formulas algebraically if you needed to compute the other. Okay. And so let's say that, you know, we are using this formula, and we, you know, we're given a uniform series of payments, and we want to see how much money is that worth in the present day. We can use this formula. We just have to take this guy and move it over there. So, you know, I gave you basically just one forms of these equations, but you know, you can manipulate them to basically compute whatever you need to from them. Okay. So that's, you know, how we compute basic equivalence between all the, you know, the basic cash flows of present sums, future sums, and uniform series. Okay. But I want to take kind of a brief aside to talk about, you know, what if you have a cash flow that doesn't fit those kind of basic patterns? Okay. Because, you know, with everything that we have so far, you know, we can do a wide range of kind of economic problems, but there could be situations where, you know, just the situation that's given to you doesn't match exactly everything that's given. Okay. And so I think the best way to do this is to illustrate this with an example. So that's, you know, that's going to be the bulk of this section. But, you know, the kind of the upshot for this is, you know, for these problems that don't fit the basic patterns, sometimes you'll have to do kind of not just one step, but two steps of calculations in order to compute what you need to do. Okay. And so you'll see what that means in this example. Okay. So in this example, let's say that you know, you take out a loan where you receive $1,000 a year from this loan. Okay. Okay. And so, you know, because this is a loan, you have to repay it. But because of the terms of the loan said you don't have to repay this until 2 years after the end of the loan. Okay. Okay. And the interest rate is going to be 15%. Okay. And so what we want to compute is, you know, in that lump sum, how much are we going to have to pay for this loan? Okay. And so for these kinds of problems with you know, kind of complicated cash flows, I find that it's always helpful to draw the cash flow diagram. Okay, so let's draw this. Right, so first of all, we have the first 3 years. My mouth said 3 and my hand also wrote 3. So in the first 3 years of this loan, we're going to be receiving $1,000. So let's go ahead and draw that in. Okay. And so that's what's going to happen for the first 3. So every year, for the first 3 years, we have a uniform series of $1,000. Okay. Right. And so what the loan says is that we can take out those monies for the first 3 years, but we don't have to repay the loan until 2 years after the end. Okay. So 2 years after the end of this will be in year 5. And so at the end of year 5, we're going to make one lump payment, at the end, right? And then that's what we're trying to solve. And so with this cash flow diagram here, we can see that it's a little bit strange because, we have a uniform series that occurs for the first 3 years. Then we have a break, for 2 years, and then we have one lump sum. Okay? And so we won't be able to solve this problem with just one kind of application of the formula that we did before, because of the way the formulas are designed. Okay? And so we're gonna do this basically in 2 steps. We're gonna first apply a formula, and then that's gonna give us a different kind of cash flow diagram, and then from there we can convert it to this payment in year 5. Okay, are there any questions on the problem setup? Okay, so the first step is, let's take this uniform series and let's convert that to one lump sum in the future. Okay. And so to do that, we can use our Fna formula, okay, because we have a uniform series, which is A, and then we want to convert that into one single lump sum in the future, which is F. Okay. Right, so our Fna formula looks like this. We have F is equal to A times 1 plus I to the n minus 1, all divided by I. Okay. And so if we plug in, A is equal to 1,000. Okay. I is equal to 15%, so I is equal to 0.15. Okay. And then since we're receiving the money for 3 years, we're going to put n is equal to 3. Okay. And so once we do that, we plug in all the numbers, we get 3,472. Okay. Okay. And so this 3,472 is one single lump sum, but it occurs in year 3. Okay. And so the reason for that is, let me go back to the beginning here. Okay. And so, we have this Fna formula. So we basically just use this guy right here. Right. And you can see that, when we use this formula and we convert a uniform series that occurs over 3 years, the F that results occurs on the last year of that uniform series. Okay. And so in this case, we had a uniform series that occurred for 3 years. And so the F that we calculated was for year 3. Okay. It's a very subtle point, but it's something that's really important, that when you're using these formulas, you want to make sure that you put them on the correct year. Okay. And so now what this looks like in terms of cash flow diagram, it looks something like this. Okay. But that's not the F that we want, right? So the F that we want is actually in year 5. Okay? And so we've done kind of the first part of the problem where we converted that uniform series into a lump sum. But now what we need to do is we need to do another conversion in order to convert this 3,472 in year 3 into a single lump sum in year 5. Okay. And so, you know, we need to use another one of our formulas. So luckily in this case, it's 2 single lump sums. And so our formula for that is our F and P formula. So we have F is equal to P times 1 plus I to the N. And so we're basically taking a lump sum that's in year 3, and we're going to be converting it over there. So we can use this formula because we're just converting between 2 lump sums at 2 different times. Okay? Does that kind of make sense on, you know, why we have to do this in 2 different steps, and, you know, why we're using this F and P formula for the second step of the problem?
Yes.
Okay.
Would you mind if you repeat it again?
Sure, absolutely. So, and so, you know, we have to do this in two separate steps, because if we look at our initial cash flow diagram here, we can see that we have a uniform series over the first 3 years, right? And so we want to convert this into one single sum, which we did using this F and A formula right here. Okay? And so when we did that, we got this number, 3,472, right? And so now we have a single lump sum that represents all our uniform series of payments. But, you know, because we're using this formula here, this lump sum occurs at the end of year 3, because this is this was the last year that we received money from that loan. Okay, and so, you know, we can represent this in the cash flow diagram with a single lump sum in year 3, but in this problem we're looking for, you know, the equivalent lump sum at the end of year 5, which is when we're going to pay off the loan. Okay, and so in order to convert this, you know, single lump sum in year 3 to year 5, we need to use you know, our F and P formula right here, which is the formula that we have for converting between 2 lump sums. Okay? And so to do this formula, we're going to set P is equal to 3,472. Okay? Our I is still going to be the same. It's going to be 0.15. Okay? And then since we're only converting this between year 3 and year 5, you know, there's only 2 years in between that. So we're going to use set N is equal to 2. Okay? All right, does that make a bit more sense?
Yeah.
Great. Okay, so let's go ahead and plug those numbers in. Okay. And so we get F, we'll call this F5 because this is the future sum in year 5. This is 3,472 times 1 plus 0.15 raised to the second power. Okay. And then what we get from this is $4,590. Okay. And so to pay back that loan in one single lump sum at year 5, you would have to pay out $4,590. Okay, so that's one way that we did the problem. So we first converted to one lump sum in year 3 and then converted that over to year 5. But that's not the only way that you could have done this problem. So I'll leave this up to you guys if you wanted to take a look again later in your notes. But you know, there's at least one other way that we could have done this problem in 2 steps and still gotten the same answer.
I have a quick question.
Sure, what's up?
So all through the months through 1 and 3, you're still paying that $1,000 payment, correct?
You're receiving $1,000. So in this problem, you're receiving $1,000 per year for the first 3 years. Yeah. That's why the arrows were up. So any arrow that's up, that's money that you're receiving, and any arrow that's down, that's money that you're paying out.
All right, that's my bad.
Mm-hmm. Yeah, it takes a bit to get used to the kind of the standards and terminology, but after a couple of weeks, it'll be kind of second nature for you guys. Yeah. All right. Any final questions on that example?
I have a question.
Sure. What's up?
How would the problem look differently if instead of being 2 years, it would be like they give you 6 months to pay back?
Yeah, then you would have to, so in this case, we were able to break it down by years. So we were able to have a cash flow diagram that goes 0, 1, 2, 3, 4, 5. But if it was by month, say you only have 6 months to pay it back, you can redraw this cash flow diagram, but instead of having the numbers be years, you can have that represented by months. And so you would basically, have a finer granularity with the time scale. And then you can use the same formulas in that case too. You just have to be careful and, if you're receiving the payments every year and then you break it down by month, you would have kind of a very non-standard cash flow diagram. But you can absolutely do that. It's just that you would have to break it down by month instead of by year.
Thank you.
Mm-hmm. All right, question. So why did we receive 15% interest on the money we were receiving and not receive 3,000 over 3 years? Yeah, so that was the 15% interest is basically the terms of the loan that the bank is giving you, right? Because the bank is, loaning you this money, so, they expect to make some money off of it over time as well. So, you're receiving $3,000 over 3 years, but then when you pay it back, that debt of $3,000 is accruing a 15% interest every year. And that's basically the money that the bank is making. Yeah, so we didn't receive a 15% interest. We're paying out a 15% interest to have access to that $3,000 over 3 years. Yeah, so the 3,472, that's if we had repaid that loan in year 3, then that's how much we would have paid the bank. It would be 3,472. So, the reason I drew it as an up arrow is, instead of receiving $1,000 every 3 years, if we receive just one lump sum of that same equivalent amount, it would be $3,472. And so it was kind of just kind of an intermediate step, just to kind of represent the same cash flows. Yeah.
I have a question.
Yeah. Mm-hmm.
Why we don't have an arrow on the 0?
So the 0, we didn't receive, in this particular case, we didn't receive any money in the present day. And so just the terms of the loan is that we would get, $1,000 at the end of each year, starting in year 1. But if we did receive any money in the present day, then that would give us an arrow on year 0.
Makes sense. Thank you.
Mm-hmm. Yeah. So yes, so going back, I use an up arrow here just to kind of represent that, we converted these 3 up arrows into just one single up arrow here on year 3. So it's just the concept of equivalence that I was kind of illustrating here. But yeah, so this 4,590, that would also be an up arrow up here, right? But in order to pay it back, we would have to pay out that same amount. So in the end, it's all kind of balanced out. Okay, so that's, how we do non-standard cash flows, okay? And so, the second to last topic in this lecture notes is we have one more addition to our cash flow family. Okay? So far we have one single present sum, one single future sum, and a uniform series of payments, okay? But there's actually one more that's actually, really useful, especially for, engineering projects, and that's known as the arithmetic gradient. And this guy has a symbol of G. Okay? G for gradient. Okay? And so what the arithmetic gradient, it's a really fancy mathy sounding name, but it's actually, not too hard to visualize. Okay? So arithmetic gradient is used to represent, a series of payments or a series of cash flows. So it's similar to the uniform series in a way, but instead of staying the same over time, what the arithmetic gradient does is that it increases over time. So the arithmetic gradient is used to represent, a series of payments that increase over time. Let me be more general. I'm going to say a series of cash flows and so the key here is increase. So if we draw kind of the cash flow diagram that represents this, okay, it would look something like this. Okay? So we'd start with kind of maybe a small amount in year 1, and then it would increase in year 2, and it would increase in year 3, and it would increase in year 4 and year 5. Okay, and so you know, you can see from this, you know, the payments are, or in this case, the benefits are increasing every year. Okay, and the amount that it increases. So if you look at this, the distance between here and here, and this is between here and here, here and here, here and here. Okay, you know, my crappy art skills aside, you know, what this diagram should be showing is that the amount that this payment increases every year is the same, and that amount is given by G. Okay, and so when you're computing an arithmetic gradient, what you're interested in is how much is our payment increasing each year. Right? So does this make sense to everybody? Any questions on this? Okay. And so now that we have a new cash flow, you know, we need a set of formulas to convert this, because we need to be able to convert G to P, G to F, and G to A. Okay? And so let me draw out the, let me give you guys the formulas for this. And so, you know, I'll say if you're interested in seeing, you know, where these formulas come from, I do have the derivations that are in the lecture notes. And so just by nature of this class, you know, everything for some reason seems to go a little bit slower on the virtual instruction, you know, which is totally fine. But because of that, you know, I have to leave out some of the details in the notes. So if you're interested in seeing how these formulas are derived, all that is in the lecture notes. But for now, I'm just gonna be giving you the formulas and kind of just showing you guys how to use it. Okay, so first let's do the formula for F and G. Okay, so we have F is equal to G over I times 1 plus I to the n minus 1 all over I minus n. Okay. So it's a pretty cumbersome formula. Right? Okay. Okay. And so there's the formula for that. And so you can use this formula to convert between one future sum and you know, at the end, and the respective uniform gradient or arithmetic gradient. Okay. And so one really subtle notational note, you know, I drew the original you know, figure here such that, you know, the cash flow starts in year 1, but the actual you know, real definition of gradient actually starts in year 2. Okay, and so you have to be careful about this when you're doing problems that, you know, you start your gradients in the same year. Okay, and the reason it's like that is because, let me redraw kind of the figure from the previous page. Okay. Okay. And so if you have a situation where you have something that starts in year 1 and then it increases starting in year 2, right? One way that you can represent this with both a uniform series and an arithmetic gradient would be something like this. Okay. And so one way that you can represent this is you can take this amount, you know, of that you're paying in year 1, and then make a uniform series for that. So you can say that this cash flow diagram at the base has a uniform series of this amount. Okay. And then to that, you can add a uniform series, or an arithmetic gradient. That starts in year 2. Okay. So it's a kind of a really subtle thing, and it's kind of a weird thing to work with at first, but you should always kind of remember this when you're doing problems. Okay, and so whenever you have an arithmetic gradient, you know, it only starts at the time when things actually start increasing. So usually things don't actually start increasing until year 2. Okay, year 0 is kind of a strange time because that's the present day, and then so year 1, that's kind of the first time that you can actually start to see, you know, if you have a payment or not. And so if you have a situation here where you have kind of a base uniform payment in year 1, you know, the way that you represent that is with a uniform series of that base amount. And then, you know, the amount that is increasing, you have that arithmetic gradient starting in year 2. Okay? So it's a subtle point, but it's something that's kind of important to remember. And we'll do an example, you know, after we finish going over the formulas to kind of illustrate this. Okay? All right, are there any questions on that?
Yeah, Professor. So it sounds like the arithmetic gradient is basically change in cash flow per year. So if the interest is compounding, why is that change linear?
Yeah, so the interest is compounding. That's right. But this is something that you're actually this represents kind of like actual money that you're paying out. And so, you know, some of the applications for this would be, you know, say you bought like an engineering machine, and you're paying out like you have to pay out maintenance costs every single year, right? But that maintenance cost is actually increasing every single year, right? Because the machine's getting older and you have to, you know, pay it more to fix it. And so one common application is, you know, say that you want to set money aside today. Say that, you know, I want to put money and just stash it away in a bank account, and then have that accrue interest over time, and then that's going to cover all my maintenance costs over the years. And so, you know, that's a case where, you know, you can have an interest rate and then have that accrued money to cover this gradient cost. It's a bit weird, but yeah, this gradient kind of represents cash that you're actually paying out, but how much that's worth, you know, because time is going on is different because of the interest rate. So I think it'll be probably more clear once we do an example, but that's kind of, you know, the common situation with this guy. Yeah.
Okay, thanks.
Mm-hmm. Okay, so that's the F and G formula. So now let's do P and G. Right? So this guy is actually pretty complicated. Okay, so we have P is equal to G times quantity of 1 plus I to the n minus I times n minus 1, right, all over I squared 1 plus I to the n. Okay. And so schematically, it would look like this. And so in this case, we're converting one lump sum in the present day with an arithmetic gradient. Okay. Okay. And then the last one that we need is our A and G formula. Okay, so we have A is equal to G times 1 plus I to the n minus I times n minus 1 all over I times 1 plus I to the n minus I. So let's just draw this schematically. Okay. And so if you're converting between a uniform series and an arithmetic gradient, this is what it would look like. And so again, these formulas are pretty, they're pretty intense. So definitely, if you want to refer to these, I think it would help a lot to, write them down on a piece of paper just so you have them ready. Okay. All right. Any questions on this before we do an example? Okay. Okay, so let's do an example from the situation that I described over before. Okay, so let's say that your friend bought a new car, and what he wants to do is he wants to set aside money now to cover all the maintenance costs over the next 5 years. Okay. And so, your friend talks to the car dealership, and he gave you this table for, how much he estimates the repair is going to cost each year. Okay. We have year 1, year 2, year 3, 4, and so what the car dealership guy says is that in the first year, the repair is going to cost $120. In the second year, the repair is going to cost $150, and third year is going to be $180, and then $210, and then $240. Okay. And so, your friend sees this and he says, this is the actual money your friend is going to pay out to the dealer every single year in order to repair your car. But what he wants is, he says, I don't really want to worry about this. I just, I have, a good amount of cash right now. I want to stash it away into account, which is going to collect interest over that time. And so that I can cover these expenses. Okay. And so the question is, how much should your friend So how much should he put away now to cover these costs if he has an account with a 5% interest rate? Okay. Okay. And so let's break this problem down. Okay. So the question is asking for how much he should put away now. And so whenever you see the words now or present day, that means we're solving for P, right? Okay. And so we need to take this information, solve for P. Let's state the interest rate. So the interest rate is 5%. And so in our formulas, we're going to plug in 0.05. Okay. And then our N, because we want to cover these expenses for 5 years, our N is going to be 5. Okay. And so let's look at our costs, right? And so our cost, we can draw the cash flow diagram for it. So our costs are going to start at 120 in year 1. And it's going to increase every year after that. Okay. So it's going to start at 120 and then be 150 and then be 180 and then 210 and then 240. Okay, so just like we talked about in 2 slides ago, we're going to break up this cash flow into 2 standard series payments. Okay, so first we have a uniform series, and then we have a gradient. Okay, so the uniform series kind of represents the base amount that's going to be in this cash flow diagram, And then G is going to represent how much that payment is increasing per year. Okay? And so the uniform series for this one is going to be 120 because that's what it starts out with at year one. Okay? And then that 120 increases by 30 each year. Okay? So we have two different cash flows going on. So we have a uniform series of 120 and then an arithmetic gradient of 30. Okay? And so what we need to do is we need to take these guys, and then we're going to use our formulas to convert them into present sums. Okay? And then once we convert them to present sums, we can add them together, and then that's how much money your friend should put away in order to cover all these repairs. Okay? All right, are there any questions on the problem setup? Okay. Okay, so we're going to apply two of the formulas. So first we're going to apply our Pna formula, right? So we'll call this P1, and this is equal to A times 1 plus I raised to the n minus 1 all over I, 1 plus I raised to the n. Okay. And then we also need to apply our P and G formula, which I don't think will fit, but I'll give it a try anyway. So you have P is equal to G times 1 plus I raised to the n minus I times n minus 1, okay, all over I squared times 1 plus I to the n, okay? Okay, and so we have everything in these formulas, so we basically just have to, it's just kind of plug and chug at this point. So let's plug in all the values for P1. Okay? And so if we plug in all the values for P1, we plug in our uniform series of 120, our interest rate of 5%, and our n of 5. What we get is P1 is equal to 520. Okay. Okay. And then we plug in all the values for P2. So we have an arithmetic gradient of 30. Our interest rate is 5%, and our n is 5. And then we do that, we get 247. Okay. Okay. And so once we've plugged in all those values, we can go ahead and just add these two guys up. And then what we get is $767. And so if your friend takes $767, he stashes it away in a bank with an interest rate of 5%, then he'll have enough money to cover all his repairs over the next 5 years. Okay? So Kit, going back to your question, the uniform gradient is used to represent, kind of the actual money that you pay out. But, as time goes on, any money that you do have is increasing in interest. And so this is how you would kind of convert, money that you have in this case today, and how, the money would grow and cover those increasing costs from the arithmetic gradient. Yeah.
That makes more sense. Thanks.
Yeah. Yeah. So the whole idea with these formulas is that, if you look at kind of the cash flow diagrams for each one, the cash flows happen at different times, right? So just in kind of the most simple case, we have a present sum and a future sum, right? And over that time, your money is going to grow in value because of the interest rate. And so you can think of these formulas as kind of computing equivalent values for your money over different amounts of time and different kinds of payment structures. Yeah. Okay.
Professor, I have a question.
Sure. What's up?
Yeah, so going back to what somebody asked about knowing what to input for n, whether it was months or years, how would we input months? Like, how would we know if it was referring to months or years? Will we enter like as a decimal?
Yeah, so you can't use decimals for n. So n has to be an integer. So what I meant by that was you would have to kind of change the language of the problem. So I think that problem was over 5 years. And so instead of having having payments that occur at the end of each year, what you would do instead is we can expand this horizon. So instead of 5 years, we can expand it to be over 60 months, right? And then you would do the calculations based on 60 months. So
Oh, that
you know,
makes
it's
sense.
yeah, it's a little bit cumbersome when you have to kind of break it up into ones like that. But it's definitely possible. And you know, if you have like a loan or something that's, you know, you have to pay back in 6 months, or you have to make monthly payments, that's how you would do it basically.
Oh, that makes a lot of sense now. Thank you.
Yep. Mm-hmm. Are any other questions on this example? Okay. All right. So there's one more topic in this set of notes, and this is the part of the class where you'll probably be really mad at me, but that's okay. And so this is you know, the last part of this notes is how to use what's called the compound interest tables. Okay. And so, you know, for the last, you know, lecture and for today, you know, we've been computing equivalent cash flows between present sums, future sums, uniform series, and arithmetic gradients. And we have these extremely cumbersome formulas to do that, right? And so, you know, in their essence, they're just kind of plug and chug problems. But, you know, these formulas are not really the easiest to use, because it's, you know, when you have kind of a long, complicated formula like this, you're kind of just asking to kind of make just an input mistake. Okay? And so luckily, you know, people have thought about this, and they've come up with kind of an easier way to do these problems, given certain conditions are set. Okay. And so the way that they do this is, you know, if you look at kind of this formula, and let me use a different color to kind of illustrate. Okay. If we kind of ignore the A in this one, and we look at just this, okay, and we'll look at just this part right here. Okay. And so if you look at those parts that I've highlighted, you'll see that there are only 2 variables in there, right? And so the only things that you need in order to compute that factor are the interest rate and the time period. And so this is true for kind of all economic problems where, you know, if you compute the, if you know the interest rate and you know the time period, you know, you can compute that factor, okay? So let's say the factor in the formulas can be computed and so the only thing you need is just the interest rate and n, and you can compute that factor, okay? And so let me actually rewrite that first equation there into a different way, which kind of isolates that factor, okay? So let's say that we have P, and I'm going to divide both sides by A. So let's say that we have P over A is equal to 1 plus I to the n minus 1 all over I to the 1 plus I to the n. Okay. And so we have a ratio of P over A, and that's equal to our really kind of cumbersome thing. Okay. And so luckily, you know, what someone's discovered is that, you know, because we only have 2 variables here, you know, why don't we take this and why don't we just tabulate it and just have it kind of in a list of big table values, okay? And so instead of plugging in, you know, I and n into these, you know, really cumbersome formulas, let's just have a table that kind of shows all these factors so that you can perform these calculations much more easily. Okay. Okay. And so actually, I think probably the easiest way is to kind of just share my screen so you can see. Okay. So let me go ahead and do that. Okay. And so this is the compound interest table. So I'm going to upload this onto I keep saying titanium. I'm going to upload this onto Canvas shortly after this class. Okay. And you can see, you know, there's a lot of numbers here, but let me kind of show you how to read this. Okay. Let's go to a better one. Okay. And so the way you read these tables, you can see that there's 32 pages in this PDF. And the way you read the table is that each page has a different interest rate that's associated with it. Okay? And so this is the page for 2%. So if your interest rate is 2%, you would go to this table right here. Okay? Next, you can see that each of the rows in this table is an n value. Okay? And so depending on your time horizon, you can go to different rows in this table, and they have a lot of different numbers. Okay? And so if your time horizon is like 5 years or 5 months, you would go to this row in the table. Okay? And then the next thing that you would look at is, what factor am I looking for? Okay? So you can see all the factors here are given as ratios, basically the same way that I presented the formula, before we kind of jump to this table here. Okay? And so the way to read this formula, or the way to read these ratios, is that there's always a value in the numerator and there's always a value in the denominator. Okay? And so the value in the numerator is the type of cash flow that you're converting to, and then the value in the denominator is the type of cash flow that you're converting from. Okay? And so let's say that you have a certain amount of money. Let's say that you have $1,000 in the present day, okay? And you want to deposit this into a bank account with a 2% interest rate, and you want to see how much that $1,000 is going to be worth after 5 years. Okay? And so you would look at your problem. You would say, okay, I have a present sum of money, so that's what I'm converting from. And so I want to look at something where P is in the denominator, okay? And I'm converting into a single lump sum in the future. So that's going to be an F right here, okay? And so you go to the F over P column because you want to convert to a future sum from a present sum. You're already on the table for 2%. And then you go to the table, and then you go to the row for the amount of time that you're going to do. So in this case, we're interested in 5 years, okay? And so that factor is 1.104. And so the way that you use this table is that you just take your P, so in this case your P is 1,000, and then you multiply it by the factor in the table, which is 1.104, and then from there you would just easily be able to calculate F without having to use the formulas at all. Okay? And so just by that, and I literally just made up that problem just now, and so from that you'll be able to compute, say that if you have $1,000 today, you deposit into a bank account with 2% interest. In 5 years, that $1,000 is going to be worth $1,104. Okay? And I just computed this just on the fly right now without having to plug in anything into a calculator. Okay? And so the compound interest tables, when you can use them, are a really powerful tool because they, they really simplify your calculations, especially for the really complicated ones that involve G's and A's, right? So you don't have to plug in 1 plus I to the n minus 1 times n, and it saves you a ton of work. So when you can use these tables, you should definitely use them because they save you from inputting a ton of stuff into the calculator. Okay, are there any questions on this? I'll do an example after this, an example or two on how to actually use this in a problem. Okay. So let me bring back my iPad. Okay, so let me actually write down the example that I talked about in the on there. Okay, so let's say that we have $1,000 and we want to invest this into a bank account with 2% interest. Over 5 years. Okay. And so we want to know how much will it be worth? Okay. And so let's break this problem down. So we want to invest $1,000 today. Okay, so that $1,000, this is a present sum. Okay, so we're going to label that with a P. Okay. I is 2%, and then N is 5 years. Okay. And so we want to compute the future worth, or the future, the lumps future sum of this money. Okay. Okay. So normally the way that we do this is we would plug into this formula, right? But with the compound interest tables, we don't need to do this at all. Okay. Okay. And so in the compound interest tables, you would look up the factor of f over p. Okay. Okay. For a 2% interest, and n is equal to 5 years. Okay. And so if we look up that value on the table, oops, you would find that f over p is equal to 1.104. Okay. And so that's from the table. And so in order to compute the future worth, we would say that f is equal to p, our p, which is 1,000, okay, multiplied by the factor in the table. So that's 1.104. Okay. And so that's $1,104. Okay. So you can see it's much easier, right? So I know, a lot of you guys are probably upset because, why did we go through all the formulas when the table makes things just way easier, right? And so, I've been mentioning that, you can use the tables when they're applicable, right? And so, if you actually scroll through the tables, you'll see that, they have quite a few interest rates. They have 31 different ones here. But usually those are going to be, your whole numbers like 5, 6, 7, 8, 9, 10. Okay. And so if your interest rate kind of matches up to something exactly in the table, you can use it. But if you're given a problem where your interest rate doesn't match up to something in the table, so say you have an interest rate of like, 8.3%, which is, a problem we did last time, then in that case, you're a little bit stuck because there's no compound interest table for 8.3%. And so in that case where you have kind of a weird interest rate that doesn't match up to like a whole number or like a nice decimal, in those cases you have to use the formula for that. Okay? And so that's why I teach you both, where like, if you have kind of a nice interest rate, you can use the table for that and it makes it easy. Most of the problems I give you in this class will have kind of nice interest rates. But when you're going out into the real world, the interest rates that that are given to you usually by the banks, and those are set by the government, those usually aren't nice whole numbers. So in those cases, you're going to have to refer to the formulas in order to do that. So it's the same process and it's the same ideas behind doing the problem. It's just that you can use the tables when they're applicable, but if not, you have to use the formulas for it. Okay. All right. Are there any questions on this? Okay, so let's do one more example with the table. Actually, let's redo the previous example, and let's see how easy it is to do it with the table. Okay, and so this is the example with your friend wanting to set aside money for his car repairs. Okay, and so what we have in this problem is we have two cash flows. Okay, so we have A is equal to 120, and G is equal to 30. And then in that problem, basically what we're doing is we were converting these cash flows into a present sum. Okay. And so our interest rate was 5%, and then the N is 5. Okay. Okay. And so we did this problem with the formulas, you guys kind of just watch, and I plugged into the formulas. But then, we can do this exact same problem with the tables. Okay? And so, since we know that we're converting to a present sum, we know that we need for this first one, we need a factor of P over A. And then for this one, we need a factor of P over G. And so we're going to look in the compound interest tables for those factors. Okay. And so you're going to go to the compound interest table for 5%. Okay. And go to the n is equal to 5 row. Okay. And so if you look up these values in the table, you'll see that this value is 4.329. And this value right here is 8.237. Okay. And so to solve this problem, you can say that P is equal to our A value, where our A value is 120, and we're going to multiply by our P over A factor, okay, plus our G is 30. We're going to multiply this by our P over G factor, okay, and so this can be 120 multiplied by 4.329 plus 30 multiplied by 8.237. Okay. And if we do that, we get 767. Okay. Right. So we got the exact same answers we did before for the formula method, but you know this involved a lot less punching numbers into the calculator. You know, this is just looking something up in the table. So you know, I'll answer the big question that I think is on everyone's mind, and which is do I care which one that you guys use for like the homeworks and the exams or not? So I don't care, because you're going to get the same answer, if you use the table or the formulas theoretically. And so I would say, use the one that's easier for you and the one that makes more sense for you. So, even with the convenience of the tables, I know some people still like to use the formulas because they feel like, it's more satisfying to do that. So if you want to do that, more power to you. But if the problem can be done with the compound interest tables, I would say just go for it. And so for me, I don't really care which method that you use, as long as you show me your work. So if you're going to use the tables, make sure that you actually write down the factor that you got from the table and say that, and actually write down, I got these numbers from the compound interest tables. But if you do that, you show me your work, you show me your process, either way is fine. Okay. Okay. Are there any questions on this? Okay. So I'm going to upload the compound interest tables to Canvas, basically right after this. Okay. And so we have about 2.5 minutes left in the lecture. So, that's definitely not enough time to start the next topic. So I'm going to end a little bit early today.
Would you mind if you go back to page 9, please?
Page 9, sure.
Yeah.
Okay. And so, one other thing, that I want you guys to do is I've just activated the minute paper for this week. So remember, the minute paper is your way to kind of, kind of just recall the previous week and see, what made the most sense to you, what was the most important, and anything that still doesn't really make much sense. And it's a chance for you guys to give feedback to me on how the class is going. So, so I just activated it on Canvas. So, the week 2 minute paper should be available to you. And it'll be available until the end of the day. So if you guys can go and fill that out, that would be really helpful for me going forward for this class. Okay? But if not, that's it for me. So thank you everyone for tuning in. Hope everyone has a great weekend. And just like Ton said, stay cool and stay hydrated because it's seems like the temperature is going to go up again. So thank you everybody. Have a great weekend. Fill out the minute papers if you have time. But if you're not, it's okay. And I'll see you guys next week.
Professor?
Yep.
Where can we find the minute papers again? Sorry, I'm at the page on Canvas.
Yeah, so it'll be under quizzes on Canvas. So if you go to the left-hand side of the screen and you click quizzes, the minute papers will be there.
Okay, got it.
Yeah, so it's not actually a quiz. It's just a survey, but it's under the quiz module. So it's not graded or anything, and your answers are anonymous. But it's I use that information just to gauge how you guys are doing as a whole. Yep, thank you guys. All right, do you have any more questions? Okay, so I'm going to end the session for the week, and I'll see you next week.